Hello everybody. So in this video I'm trying to show you how you can go about finding the maximum shear stress. So basically you want to take the transformation equation that you had for the shear stress, this guy, right? And remember we had our two-dimensional stress element, plane stress, no z component of normal stress or shear stress. They're all zero. So we went from a three-dimensional stress element to a 2D stress element. So this was the equation for the shear stress at some angle theta. So part of those transformation equations that you saw in the previous video. So the objective now is to find the maximum tau x prime y prime and then call it tau max. So how do we do that? Just like the way we did it with the sigma x prime, and we got the principal stresses. So we take the derivative of tau x prime y prime with respect to theta, set it equal to 0 to maximize it. So the derivative of sine 2 theta becomes 2 cosine 2 theta. The derivative of cosine 2 theta becomes minus 2 sine 2 theta. And then we'll do exactly what we did before. We can divide, for example, here by cosine 2 theta, right? And what we'll see is that this is getting cancelled, and this guy, by the way, the 2's get cancelled here, and this becomes tangent 2 theta, which eventually I call it tangent 2 theta s. And when you clean it up, it becomes negative of sigma x minus sigma y over 2 divided by tau x prime. Notice there is a negative in the front. Okay, so why did I call it theta sub s? Because this theta sub s is the angle or the plane at which shear stress becomes maximum, and that's a very important angle. All right, so now we want to go ahead and find the actual maximum shear stress here. So how do we do that? How do we determine that maximum shear stress? So we just have to plug in sine 2 theta here and cosine 2 theta here. Again, we have the same problem. We have tangent 2 theta s, but we don't have cosine or sine. But again, the remedy is what I showed you before. Make a triangle, call this angle 2 theta s. And since we have the tangent, which is opposite, here is the opposite, over adjacent. Then remember, I called this hypotenuse r. By the way, when you square a negative, it becomes positive. So it becomes exactly what you see here. So again, why did I call this r? Because that r happens to be the radius of the Mohr circle, which we'll talk about later on. Okay, go ahead and find sine 2 theta and cosine 2 theta, right? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And then plug these in here. So this goes right here. And this guy goes right here. If you clean it up, guess what? Tau max becomes exactly r, which is a square root of sigma x minus sigma y over 2 squared plus tau xy squared. So later on we'll see that the maximum shear stress actually is equal to the radius of what we call a Mohr circle. Radius of. And we'll get to that soon, within the next week or so. Okay. So let's go to the next page, and I want to show you a relation now between this angle and the principal angle. Remember the theta 1? Remember theta 1, tangent to theta 1 was tau xy over sigma x minus sigma y over 2. And now we just got tangent to theta s. Look at the relation, guys. This guy is negative inverse of this guy. If two lines, their slope is negative inverse of each one. So for example, if this is 5 over 6. The slope is 5, 6. The slope of the other line is going to be what? 6 over 5, right? If that's the case, and they're negative inverse, they must be 90 degrees to one another. So what does that mean? The difference between 2 theta p or 2 theta 1, as I called it here, and 2 theta s is what? 90 degrees. When you divide it by 2, the difference is 45 degrees. So in other words, we don't even have to solve for theta sub s. After you get your theta 1 from this equation here, just add or subtract 45 degrees to it, which means go clockwise or counterclockwise. And that gives you the plane at which the maximum shear stress is the plane at which the shear stress is maximum. So plane of the maximum shear stress I wrote here is 45 degree at 45 degree angle clockwise or counterclockwise from the plane of principal stresses. And finally, I showed you here in this picture that if this is our initial stress element, look, if you find theta 1, and theta 1 actually is measured from this vertical axis here, where we are here, and then we either go clockwise or counterclockwise. Remember, positive, if you get theta 1 is positive, that means go counterclockwise. If theta 1 happens to be negative, we go clockwise. All right, so then remember on that plane, sigma 1 and sigma 2 will happen, and there is no shear stress here, right, or here. The maximum shear stress would be what? 45 degrees added to what? Theta 1. This is theta 1, 45 degrees. So if you draw the diagonal of this rectangle or a square rather, you get the plane of maximum shear stress here. So maximum shear stress, as you could see, is happening here. And now it could be shown actually there would be a normal stress here, and that happens to be actually our average stress being, you know, the average of the normal stresses. So remember, your principal stresses were what from the previous video is sigma x plus sigma y over 2, or the average stress, plus what? Plus or minus the square root of, actually this is the maximum shear stress right here, right? This is R, the radius of the Mohr circle, which we'll talk about later on. Okay, hopefully I will show you an example with numbers, and things will clear up in that example. Again, thank you for watching and listening.